Welcome to a quick prototype of the workflow I'm planning to use in chemistry. By no means is this a lesson, but it is meant to give us an idea on how this workflow will integrate between this camera and Edpuzzle and kind of the digital learning I'm hoping to implement during this COVID social distancing thing. So today I want to talk about oxidation reduction. And oxidation reduction is something we've actually been seeing for a while. As you can guess, it involves both oxidation and reduction. And most chemists don't actually call it by these names. We call it a redox reaction. And these are everywhere. They're the thing that drives so much of what we've been seeing over the past week's reactions, and they're really quite straightforward. In a redox reaction, what we're doing is we're moving electrons from one element to another, or more properly from one atom to another. And we're moving those electrons. The act of moving that electron actually creates the reaction. And it's a really powerful thing to understand. So our goal for the next couple days is going to be to work through what's a redox reaction and what's actually happening when they're reacting. So let's start off by kind of putting this in context, right? If we're studying redox reactions, we've got to be starting with something we've already seen. So let's take a look at the reaction between potassium and chlorine. And we've just been studying these kinds of reactions, so what kind of reaction is this? Right now, a question should pop up in the corner in just a moment. And I think you have to click it for me to keep going. Let's try that. So I thought it'd be neat to quickly look at the reaction that's actually going on here. Here, chemists going to heat a piece of potassium metal in this broken piece of crucible or a Bunsen burner. And in the background, you might see a yellow glow in a cylinder. That's sodium reacting with chlorine. But here, this chemist is heating up the potassium, and you'll see it start burning red-purple in the top. So it's actually reacting with oxygen right now. And that chemist is going to take that burning piece of potassium metal and lower it into the cylinder of chlorine, and it creates quite a violent synthesis reaction. Quite neat to see. So pretty clearly this is a synthesis, right? I have an element and an element being smushed together. And that is true. It is absolutely a synthesis reaction. But if I take a step back, or maybe a step even closer in, how you want to talk about it, something more is going on here than just elements getting smushed. I mean, these two things were perfectly happy existing by themselves, and now they're happy bound together. Something has to change between these reactants and these products, right? And for that to happen, it's good to kind of take a step and look at the things as their individual atoms. So what's going on in this reaction is I've got potassium and chlorine, and for simplicity I've just drawn the chlorine as one atom, although it would be diatomic in real life. And together they're making like K plus and Cl minus. It's the fact that that plus and the minus, they want to stick together, right? Because opposites attract. That actually holds this molecule together. But if I think about it, there's no pluses or minuses over here, so it's kind of weird that all of a sudden there are pluses and minuses on the product side of the reaction, right? And what had to happen, of course, is that like K had to give an electron to chlorine, right? In the back of our mind, we already kind of know that, but this reaction, even though it's a synthesis, is also an oxidation reduction reaction. Now, I don't expect you to understand this right off the bat, but if you can see, we're doing things where the charges change across the arrow. If the reaction is making electrons physically move from one place to another, that's the game we actually get to play for a while. So, really quickly, let's actually define what we're talking about here. We are talking about oxidation and reduction. And right off the bat, this is pretty confusing to me. After all, oxidation is labeled the loss of electrons, and reduction's the gain of electrons. As a matter of fact, let's check in for a moment. Let's make sure you actually see this. What does it mean to reduce something? But reduction to me means to get smaller, and gain means to get bigger. And these two things seem to be exactly opposed to each other. And I remember being really, really confused the first time I learned this. And if I'm not careful, I still can confuse myself. But there's an important fact that I want to remember, and that's that electrons are negative, right? We've talked about how the molecule, or the atom, or whatever we're dealing with, is comprised of nucleus, or nuclei, where you've got all the plus protons really close together with the neutrons, and then there's this like cloud of electrons around the outside. But the electrons carry the minus part of the charge. And so if I gain electrons, if I add electrons to my atom, well then of course the charge is going to get more minus. that is, something is going to go down, right? Getting more minuses means something's getting reduced. And if I somehow get rid of these pluses and leave all those, or these electrons, excuse me, and I leave all these pluses behind, of course the number is going to go up, which is the opposite of reduction. So something with pluses and minuses must be what we're dealing with. And really, you kind of know this. Like if you had an algebra problem where you had like 4 minus a minus 2, in your head you know, oh yeah, I'm taking away the minus things. Of course the number's got to go up. But it's still confusing a little bit. And there are lots of ways chemists try to teach this to help you remember that oxidation is loss and reduction is gain. And all work. But for me, if I want to actually kind of get this in my head, I use this mnemonic, which is Leo goes grr. So losing electrons oxidizes and gaining electrons reduce. So if I'm stuck and I'm thinking, oh, is this oxidation or reduction? I'm going to remember Leo the lion says grr, that L-E-O-G-E-R. And I think this works really well for people. So when you're thinking about, oh, what's going on? Well, I have to think Leo goes grr. And to the point where I'll actually write on your problems for a while, Leo goes grr, to remind you of this fact. And I think this is a lot easier to remember than that. Even though, honestly, they're the same exact information, right? But for some reason, Leo goes grr works better than me writing it this way. Now, to do this, ultimately we're going to deal with something called an oxidation number. And this is where our game is going to start off for the next couple of weeks. An oxidation number is just a number we assign to an atom or an element, or however you want to think about it, one item within a chemical reaction that's going to describe the changes of the electrons inside of that reaction. And these numbers and determining them is the first goal of the class. Once we know this works, once we know this way of learning and this camera method works, this is where we're going to start off. Because to understand oxidation reduction, to understand these redox reactions, we have to understand oxidation numbers. So a lot of the math in this chapter is going to look something like this. These green numbers added to the top, of this reaction describe something about how the electrons within this atom are changing, their oxidation state. For today, that's all I really want to talk about. I want to just make sure that this thing works together and that this form of working is a little more engaging than like an explain everything video. So I'm going to ask you a couple quick questions up on the side here, but for today, that's all I want you to see. Talk to you soon. Bye.